welcome to our talk. We're going to be talking about conjuring events out of thin air, a bit of a brief intro to CDC. So we've got an introduction going through what CDC is, why it matters, some tool selection options, how to process and query streams, and then finally some more complex stream processing concepts. So let's present Bali Boho's ultimate in Australian holiday couture, right? It's your typical e-commerce site. People can find the gear they love, hopefully add it to their cart, all goes well, check out, and give us some money. We've got a bespoke e-commerce site, Next.js, for our front-end, API gateway for Lambda, and Aurora S3 for persistence. So our app interfaces with an inventory and accounting system, think something like Xero, and we're selling stuff to retail customers. These are people who hit up our website, while internal sales teams sell to affiliates. These are businesses that on-sell our shitty product. So can you say that? Okay. So while we're selling our merch through multiple channels, our purchasing team keeps an eye on the stock levels and work with wholesalers to make sure we don't run out of stock. So we're currently running a daily job to push information about our customers to the inventory system, and this presents a somewhat obvious challenge. We've got a 24-hour delay, which means our inventory stocks are always out of date. A burst in sales from a newly onboarded reseller or a spike in demand means that a lot of customers aren't getting their orders in a timely fashion, or worse yet, at all. So we're also giving our marketing team a daily extract of orders, which means our marketing and CRM tools are out of date. We're missing opportunities for automation. We're not sending out promotional codes to push sales over the line. And who knows what our customers are removing from their carts? We've got no idea. And our database is now what we lovingly call a fragile monolith. So all of our analytics queries, extracts, data syncs, new features put pressure on that single database. And this in turn causes our front end to become really laggy and unresponsive. And it also contributes to higher compute cost, which leads to some unpleasantly large bills. So what is CDC and how can it help? Let's start with what it stands for. So CDC can help turn a database changes into real-time business events. And if we track changes made at the database level, then what's to stop us from capturing these changes as events? And CDC helps us capture granular changes. So think individual row-level modifications as they're committed to the database. We do this by emitting an event that captures the salient details of the change. It also enables real-time reactions, which allows downstream systems like our analytics platform, microservices, to respond immediately to updates without waiting for slow batch processes. It also avoids database strain, so efficient CDC methods, especially log-based methods, prevent the need for downstream systems to constantly query the source database. And this reduces performance impact. It also decouples systems, so the source database doesn't need to know about the systems that are consuming changes, and consumers don't need direct access to our single production database. It also provides rich context, so change events typically include metadata like the type of operation, an insert, an update, a delete, timestamps, and often, and most notably, the change data itself. So let's talk about our application architecture briefly. So Marshy here accesses our e-commerce site using their favorite web client, which issues requests to API gateway, and uses Lambda to interact with Aurora. And here's the ERD for our database. Pay close attention to the orders and the products. And we've got a join between these two tables. You've seen this before, like an order product table. In this example, we're using AWS DMS to track changes to our Aurora database. DMS, which we'll talk about later, monitors row-level changes in our database and emits a CDC event as a result. And this is the first step to breaking out of the toxic integration patterns we saw earlier. You still remember the nasty CSV file export and the daily sync job, right? So let's look at a more detailed example. Our journey starts with the user adding an item to their cart. Here's the resulting API call. The application backend receives the request, translates it to a series of SQL statements, and modifies data directly within our Postgres database. Here we're inserting a new row into the order product table you saw earlier, updating the stock level accordingly. DMS detects both of these changes, and it emits a CDC event that describes the insertion of a new row into that table, and a CDC event that describes the change in the stock levels. We just sold an item. So why bother with CDC? Well, first, it gives us faster time to value. We can access real-time data changes in weeks or months instead of waiting for the years it would take to rewrite our application from the ground up, and not to mention the nightmarish migration that goes with that. It's cheaper, like we can avoid a massive investment in rewriting the app. We can focus on our effort on data integration and consumption. It's less disruptive. It's always best to minimize, impacts on a stable legacy system. Log-based CDC reads changes non-intrusively, right? And it avoids risky modifications to our legacy application code, which you should stay away from. It also takes a slow burn approach, right? So we can modernize our app really sort of at our own pace. We can build new event-driven features, real-time analytics, microservices, using the streams that we produce from the legacy system. And it allows gradual evolution rather than like a big bang approach to replacing those systems. And last but not least, it helps make use of our data now. So with CDC, we can make critical data that's locked away in older monolithic legacy systems readily available to cloud platforms, data lakes, downstream applications without complex source code changes. So I'm just going to hand over to Ben to talk a little bit about how we can realize the CDC pattern, starting with Amazon DMS.
Yep, thanks, Rami. So starting with Amazon DMS, how does it work? Well, it uses the database's underlying transaction log, and it supports a wide range of relational databases hosted on RDS or Aurora. So DMS handles the setup, patching, and scaling of the underlying replication instances, and it can handle a wide range of AWS services to consume downstream, such as S3, Kinesis, Redshift, MSK, OpenSearch, Lambda, plus many more. It also captures changes from one database, so say Oracle, and it can replicate them to another one like Postgres. And the schema conversion tool in DMS helps migrate schemas between different database engines. A DMS task defines the end-to-end behavior of a data migration or replication job. The task has three components: a source endpoint, that's the origin DB, a target endpoint, that's the destination database, and the migration settings. These define the type of migration required and how it should be carried out. There are three types of migrations we can carry out. Full load migrates existing data once. CDC only, which captures the ongoing changes, inserts, updates, and deletes. And then there's full load in CDC, which first copies all of our data and then passes through the changes after that. So let's look at the DMS rules. These allow us to define the changes we're interested in tracking. Selection rules are mandatory. Without them, DMS won't know which tables to process. So here we've defined a rule called include product table. It includes the product table for the e-commerce schema on our database. So another option is DynamoDB. While it doesn't have rules per se like DMS, it does have a native support for CDC through a feature called DynamoDB Streams. This gives us native integration within DynamoDB, allowing us to capture a time-ordered sequence of item-level changes within a DynamoDB table. With DynamoDB Streams, we're fully managed and serverless. There's no infrastructure we need to provision or manage for the stream itself. Changes appear within the stream, typically within seconds, and we're guaranteed the sequence of events within a partition key. We can configure the event payload. We'll take a look at this shortly. And it's very common to trigger Lambda functions directly off of the stream for event processing. DynamoDB Streams makes this very easy with a seamless Lambda integration. So let's take a look at some configuration, particularly the stream view type parameter. This is the most critical choice as it determines the content of our change records. Our options are keys only capture the keys of the modified items, so minimal size, low detail. New image captures the full item after the change. This is useful when we're doing replications. Old image capture the full item before the change, so think auditing, deltas, and UN old images, which gives us the best of both worlds. This is the highest resolution possible and obviously the largest in size. So the choice you'll make will affect your event size, consumer read costs, and the data available when you're processing the event stream. So let's take a look at keys only. If you primarily need to know that an item has changed, but not necessarily the specific details on what has changed, keys only is your choice. So let's look at some use cases. Simple cache invalidation, say you wanted to send a signal to invalidate a cache entry based when a primary key's changed. Or to trigger a generic notification to a downstream workflow if an item's been inserted, modified, or deleted. So for example, I get a notification that order UUID 456 was updated. Maybe we need to kick off a process that needs to know that an item was created or deleted to potentially manage related resources or counters elsewhere. And finally, penny pinching. When an event size and read costs are primary concerns, this is your option, and you can always perform a get item call with the key that has changed. Next up, let's take a look at the new image option. If you want the complete state of the item after the change to be available directly in the change event, then this is the option for you. Let's take a look at some use cases. This is useful when you're copying the current state to another system, like a data warehouse, Redshift, or OpenSearch. Or if you need aggregated views or some other data structures to keep up to date with the latest information. Or maybe we're just sending the most recent item data to display to users. If you need to ensure that the search service has the current indexable content of items on hand. And finally, if you have an aversion to making get item calls, maybe your consumers almost always need the full item content after a change, this is the option for you. Now for the old image, you want to use this setting if your focus is understanding or acting upon the state of an item before it was changed or deleted. Do note this is not available for insert events for obvious reasons. So let's take a look at some use cases. Log in the state of an item before it was modified or reviewed. This is good for compliance and historical tracking. When an item is deleted, you may want to use the information from the previous state to clean up associated external resources. Think of an S3 object key that may have changed. We might want to clean that up from the bucket. If you have a previous state and you're able to fetch the current state separately to compute the difference. And finally, having the prior state might help you in design and logic to revert changes, although this can be a little tricky. Finally, both new and old images. But why would we ever need to go down this route? Well, take this road if you need the context directly within the event stream. This gives you both the state of the before and after change. And some use cases to send it home. This is great when we need to know exactly that, say, field X went from value A to value B. So when we need to compare old image and new image directly with consumer logic. So stock decreased by 5. We see the before stock and the after stock. Maybe triggering different kind of actions based on how the data changed. So say if order status changed from pending to shipped and we only wanted to get notified when that change occurs. And finally, it also helps when downstream systems need both states to perform transformations or handle potential conflicts. As this probably goes without saying, having both states is invaluable and understanding how data evolved over time. And it has to be said with this approach, it provides the maximum detail and results in the largest event sizes, so keep cost in mind when you use this one. Tread carefully when you're using streams. Filtering and routing are handled exclusively by your consumers. There's no built-in stream filtering, so your consumers have to filter the events. And there's no built-in routers, so consumers have to target a specific stream ARN. And for consumer integration, it's recommended that you use Lambda. You'll need to configure these Lambda triggers, think batch size, concurrent batches per shard, retry attempts, and probably whack a DLQ on it for error handling. An alternative to Lambda is Kinesis client library, which pushes it to a Kinesis stream. We'll take a look at this a bit later. And there are some inherent behaviors that you will need to take note of, such as the events are only retained for 24 hours within the stream, and strict order is guaranteed only within the same partition. All right, I'm going to hand it back over to Rami to talk about something.
Where's my slide?
Stream processing.
Thank you.
Yes.
All right, cool. So let's take a little bit of a talk. Oh, well, there we go. Let's talk about stream processing. So we've seen CDC turns low-level data operations into events, like this event that tells us that we've inserted a new row into our order product table. Basically, our customer added the product to their order. Or this event, where we're about to update the stock levels for a specific item in the product table. We've just sold a couple of units. So why should we bother processing this stream of events? Well, say you want an event that contains information about the entire order and not just the single product that was added to that order. So, or we wanted to see the events that showed a change in product stock levels, ignoring changes to other attributes like the price of a product. Or maybe an event every time we've sold 100 units of a particular item. So to query events, they'll need to be published to an event streaming solution like Kinesis or Kafka. And we'll need to convert the events from simple deltas to meaningful business events. So why should we bother transforming our stream of change events into business events? Well, for one, querying streams is difficult, right? It's easier to consume from topics and queues than it is to query a stream. And business events naturally represent domain events of a particular state that calls us to action. And it's a good idea to decouple ourselves from the low-level change data capture mechanism. So we'll pump our deltas or change events into a Kinesis stream, transform these changes into business events, and publish them to a relevant topic, and finally integrate those events with our downstream systems like our finance or inventory platform. So with Kinesis, we get a stream of change events. We can transform the deltas into business events, like in our previous example. We can take that insertion into the product table into a stock level changed business event, which we feed into our inventory management system. And we can query our business events. For that, we've got a few options. We have Lambda, and Lambda integration with Kinesis is achieved using event source mapping, ESM, which is an internal AWS mechanism that allows us to trigger Lambda to process records from a Kinesis data stream without any polling code. I have to stress that. All of our processing logic is contained within our Lambda function, which receives batches of Kinesis records, decodes the JSON payload, performs filtering, mapping, enrichment using the AWS SDK to call Dynamo or S3, whatever you want, and applies any relevant business rules. And when it comes to Lambda, there are some common use cases. We have stateless transformations like field renaming or simple filtering, lightweight enrichment, where we call other AWS services, and we can trigger downstream notifications or workflows based on a specific change occurring. And basic stateful processing, when using an external store like Dynamo, you kind of have to be careful. You'll need extra external persistence, right, to manage state across invocations. And there's a maximum 15-minute execution time limit per invocation, as you know. And you have to watch out for cold starts if you're processing or handling events that occur infrequently. So let's take a look at an example. Here we're looping through each record we receive from a Kinesis data stream. Each record contains a base64 encoded DMS change event. We extract and decode the payload. Here we're pulling out the metadata, table name, operation, and the data, the actual stuff that changed in the row, SKU or stock level. And for some filtering, we now only proceed if it's a data change event, so not a schema change or a control event. The table name matches product, the operation is an insert or an update, and the data payload is present. So next we extract SKU stock levels. And finally, we call a function that's not shown here to publish that event to an SNS topic. And this message could notify other systems or trigger some downstream processing. And finally, we have Kinesis Analytics. So for integration, Kinesis data analytics applications like SQL or Apache Flink can read directly from one or more source Kinesis data streams. And as far as the processing logic goes, for standard stream analysis, we can use SQL or Apache Flink for more advanced custom processing. And our processing logic runs continuously in a fully managed environment. So here we have a customer placing a new order, adding an item to that order, adding another item to the same order. And what we want to do is we want to create two business events, one for each item. So we can join information about each product that was added to the order to details of the customer that placed the order. And this gives us a business event for each item we ordered enriched with those customers' details, in this case, the customer's ID. And here's what Kinesis SQL looks like. A pump in Kinesis SQL pushes data into a target stream or table. This one creates or replaces a pump that inserts enriched records into an enriched order lines output stream. The main select statement extracts the order line information and joins it with the order header and gives us customer ID and order status. And finally, we have the window joined with the order stream. We'll talk about windowing in a second. We perform a left join to include all the order line records, even if a match in the order header stream isn't found. And the join is done over a time-based window. So here we create a 1-hour sliding window that groups order header records by the order ID, and it considers only those that arrived in the last hour. So this helps match events that may arrive at slightly different times due to stream asynchrony, which is another nightmare we'll allude to later on. So streams aren't a silver bullet, and Ben will tell us exactly why.
All right, so there's some challenges with streams. In a stream, events never stop. So how do you group events together in a meaningful way? That's where windowing comes in. So we use windows to define a time-based boundary around events. And different windows help us solve different kinds of problems. So fixed or tumbling windows are really good for hourly summaries or end-of-day reports, think your dashboards. Sliding windows are really good for detecting trends and changes that evolve over time. And finally, session windows are really good for capturing human behavior like browsing, shopping sessions, but we won't go into detail about those ones. And it's these windows which give us the underlying stream processing engine manageable into logical chunks of data to work with. So here's an example here of a tumbling window with a window size of 10 minutes. Each interval on our timeline is 5 minutes long. So a 10-minute window sits neatly over 2 blocks. So the first window here contains 3 orders worth $4, $2, and $8, giving us a total of $14 in the first window. We then shift to the next 10-minute block, and we just have a single order worth $1. And the final window, we have a single order worth $9. Now, let's take a look at slide-in windows. These behave differently. The window doesn't jump between a discrete amount of time. It continuously moves across the stream, say every second or every time we get in a new event. This makes it perfect for an analytics task, like triggering an alarm when the number of total orders in the past 10 minutes falls below 3. So if we slide it along by 5 minutes, we see we still have 3 orders, and pay attention to the fact that we've included these 2 orders in the last window. So it's sliding across. It's not 10-minute chunks. It's continuously moving over. Now, sliding the window another 5 minutes down, we find that the total number of orders in the last 10 minutes is 2. An alarm is now triggered because there was less than 3 orders in the past 10 minutes. So let's consider the difference between event times and processing times. Starting with event times, they represent when the business event actually occurred at the source. These times are usually embedded within the event data, so database transaction commit. They represent a historical fact of the event itself. As for the processing time, this is the timestamp that's recorded when the event processing system observes or handles an event. So think when it lands in Kinesis. These times are available, influenced by ingestion, latency, network delays, queuing, system load, clock skew. So there's a lot of things that can happen. So we've got a problem to solve. What happens when the events are late? In real world, events can arrive out of order because of networking issues, retries, processing lags. Think about IoT applications and mobile apps. Without handling this, we'd misplace events or miscount them. This is where watermarks come in. So think of this scenario. Say we have an event representing a financial transaction. To get an end of day report for the processing time, the accurate event time affects business decisions like dynamic pricing, inventory restocking. A customer might have to place an order, then cancel an order. If these are processed out of order, we won't restock the right item. If our event arrives later than the exact time it occurs, then it won't be counted in this cutoff for end of day financial and inventory processing. So let's see how we can use watermarking to solve this. Say we had all events between 0 past and 5 past. An event won't be processed if it arrives outside the processing window. Now, here's part of the stream that scares me, watermarks. So a watermark is a best guess about data completeness based on an event time. So it's a bit like this. Based on event times I've seen so far and allowing for some delay, I believe I have received all events up to the time t. So how do they work? Let's start the streaming engine and decide when it's safe to close the window. With late events that arrive before the watermark still being processed, but late events after the watermark are discarded or flagged as late. And by not closing a window too late, we ensure accuracy. And all of this goes without saying, this can get real messy. So let's hurt ourselves with a quick example. So you see the processing time progressing linear. You see the event times, they're all out of order, jumbled. Like this one's really late. And we've got a watermark progressing. So take this simple watermarking strategy. We get a watermark every 5 minutes. And say I want all orders between 0 minutes and 5 minutes past. So we look at all the events produced between these 2 times. So we select all events up to the watermark, filter out any events that don't fall in that time frame, giving us a total of $6 worth of orders. Be careful when selecting your watermark strategy, as it can be very late. So to fix this issue, you may have to create a process to handle this really late arriving event. So pick a good watermarking strategy. So let's wrap it up. CDC acts as a bridge between operational databases and real-time analytics. CDC supports better business decisions with immediate data insights. It helps us avoid information loss. Tool choice impacts ease, scalability, and maintenance. And stream processing Kinesis Windows watermarks ensures reliable, accurate analytics. So look, if you had one shot, one opportunity to seize everything you ever wanted in one moment, would you capture it or just let it slip?
Thanks, Ben. Is there a Q&A?